carry propagate adders are basically, we're taking the concept of the full adder design for a single bit, and now we're translating that into a multi-bit adder. And so if we have an n-bit adder called a carry propagate adder, we have n bits of an A input, so A n sub 1, n to 1 number of bits, and B input with n number of bits from 1 to n. And we want to now add A and B together with a carry in, and then generate a sum of n bits from 1 to n number of bits, and a carry out. So in this case, with normal addition, each sum bit depends on all of the previous carries. So bit 2 depends on the carry coming from bit 1. Bit 3 depends on the carry coming from bit 2, which depends on the carry coming from bit 1. So in effect, if we have an n-bit adder, we now have to compute n number of carries, and those need to be done sequentially, or at least one potential consequence is doing them sequentially. So looking at the lower left, you can kind of see the that's the kind of the symbol for an adder is something that looks like that, where you have kind of looks like a muck structure, but has a little V in the middle between the two different inputs, A sub n to 1 and B sub n to 1, and then kind of being scrunched together to the sum n sub 1 on the output. And on the right hand side is an example of if you had a 4-bit adder and you were adding the numbers 1111 to the number 0000. Depending on what your carry in is, if you have a carry in of 0, you just get 4 ones out. If you have a carry in of 1, then each bit will give you a sum of 0 and then a carry going to the next bit of 1, and then 1 plus 1 gives us a 0 sum out with a carry going to the next bit. And so you can see that the carry has to propagate through every single bit in this particular case. So the question is, how do we wind up doing this computation for these carries as quickly as possible? Because obviously the longer it takes, the slower your frequency of operation can be. So we'll go into various different types of adders, carry propagate adders you can create, and how to create ones that might be faster than others, and the pros and cons of different carry propagate adders. So the simple carry ripple adder is basically our simplest adder design. This is basically taking a cascade of our full adders, so whichever full adder design that we want to choose from the previous ones that we've gone through. If you just take each individual stage and cascade our C out from that stage to the C in of the next stage, bit 2, this allows us to make a functional design. It works, but this will be the slowest carry path. I mean, like I said, you have to go carry in through carry out of each bit in order to get all the way through. So if you have a 4-bit adder here, the carry has to propagate through each bit successively, and you have to wait for the previous bit. So you basically, this is a simple design, but it's a slow design. So we'll look at different techniques to try and basically make a faster design than this, because for very large data paths, you can't wait for this amount of delay through them, or you're going to be operating very, very slowly. One technique to speed up the delay from the previous version that we talked about on the last foil is to keep track of your inversions. So the previous version showed we have a C in and we have a C out that's a non-inverted version. If you remember looking at a lot of our basically the designs of the adders 1, 2, and 3, when we're not talking the full rail dual rail domino design, each of those versions, if you had a C in coming in, you would get a C out bar because of the way that for a fast stage, if you just do a single stage, our complementary CMOS, you get every stage is typically inverting. So when you have a C in, you get a C out bar, you have to add an extra inverter in there to get C out non-bar. So this is showing, well, what if we created stages where we have one stage that takes C in, it gives us C out bar, and then we make the second stage actually accept C out bar as its main input, and then it generates a C out, which is our second carry bit. Every other carry bit is going to be either even or odd, and you just keep inverting it stage by stage. So this can eliminate an inverter as compared to our normal full adder. If we use the same full adder for every bit, if we use an inverted version of the full adder, and we know we're implementing C out versus C out bar, we can actually remove an inverter from every stage for the carry. So this can speed us up by possibly a factor of 2, but we still have to wait for the carry to propagate through bit after bit. And for a smaller adder like an 8-bit or maybe a 16-bit, the speed up of getting rid of one inversion per stage might be good enough for you. Typically for a 128 or 64-bit adder, you're still going to want something else to speed you up some more. So all of the next techniques that I'm going to be talking about will make use of this function that's called PGK for adders. So for an adder, like we said, for a full adder, we want the carry is the most critical thing. And so we want to define what happens to the values of your carry out and your sum in terms of if basically for any given bit after about the second or third bit, the values of A and B are already known. They're sitting there, it's waiting for the carry to come in. So if we can have anything that depends on A and B, it calculates something in terms of A and B, and then we've got a value sitting there waiting for figuring out whether your carry is a 0 or your carry is a 1, and that way we can allow the carry out to go into out to go really quickly if we pre-calculate things based on A and B. So here's where the concept of a generate, a propagate, and a kill come in. So if we look at whether we want a carry out to come out in terms of just A and B, we can say when we look at A and B, do we know for sure whether a carry out is going to come out irregardless of whether your carry in is a 0 or 1? And one of the ways you can look at it and say yes, regardless of what C in is, you will generate a carry out if both A and B are a 1. So if for generate, we can generate a carry out immediately if A and B is true, the logical value of A and B. So we can create this other intermediate value called G that is the value of A and B. And so if we know that G is true, we can send a carry out immediately. We don't need to wait for carry in to come in. Second thing is, how do we figure out if we do need to propagate the value of carry in to carry out? And that would be true if the XOR of A and B is true. So if either A or B is a 1, but not both of them, then we know we need to wait for carry in to come in to see if carry in is a 1 to decide whether to send a carry out. So if A XOR B, so if one of them is a 1, then we know we have this propagate value that's going to be a 1, and we need to wait for carry in to come in to determine whether carry in gets propagated through. And then finally, if we can have this value called kill, which is again independent of carry. So is there some value of A and B that no matter what the value of carry in is, your carry out is going to be 0. So we're going to kill carry out. And so that would be true if A and B are both 0, then we know that it doesn't matter what carry in is, we're going to send a carry out of 0. And so the value of that would be not A or not B. So if both of them are 0, then we're going to send a value of 0 out. And so the kill would be true. So you might say, now that we know what PGK is logically, you might ask, okay, how does this propagate, generate, kill stuff actually help us in designing an adder? Very good question. I'm glad you asked. So let's go into how, if we take the previous equations where we were just talking about sum and carry and factor it into equations based on generate and propagate instead, how could this help us? So let's say we want to calculate the generate function or the generate value for some basically spanning bits I through j. And just as an example, let's say we say I is, we have a 16-bit adder and we want to know the value of generate from bits 8 through 1. So 8 all the way down to bit 1 coming in, or even bit 0 based on if we have a carry in coming in from a previous set of bits. So 8 to 0, we want to know what generate and propagate is based on all of those bits going up, from 8 to 0. So if I is 8 and j is 0, let's factor it into a smaller subset, two groups of a subset, and let's say we want to say the value of a k, an intermediate value of k is 5. So we want to look at it in terms of something between 8 and 5, and then the lower order bits on down. So we could say the generate from 8 to 0 could be the generate bit from 8 through 5, ORed with the combinational value of the propagate value from 8 to 5, ANDed with 5 minus 1 is 4 to 0 of generate. So if we take the propagate from 8 to 5, ANDed with the generate coming from 4 to 0, the lowest order bits of this 8-bit value, and then OR that with the generate from 8 to 5, then we can get the overall generate value from 8 to 0. Likewise, for propagate from 8 to 0, we can take the propagate value from 8 to 5 and OR it with the propagate value from 4 to 0. So we can now break down, instead of waiting for something, let's say, to propagate all the way through bit by bit, we can calculate these values on chunks of, like, let's say 4 bits at a time, and use the combination of those 4 bits to do just a single function to get the overall 8 bits. So now that we know the general equation over a range of bits, let's look at, for example, the base case of just a single bit. For the generate from I to I, it's just generate sub I. So for any particular bit, like bit 8, the generate for bit 8 alone is the A value from bit A ANDed with the B value from bit A. And so we had covered that in previous foil. And the propagate from I to I for bit 8 is the propagate just for bit 8 is the A value for bit 8 XORed with the B value for bit 8. So if we're looking at just bit 0, the base case for bit 0, G sub 0 is our carry in. So it's the carry in from, from some other lower order or a previous equation or something like that. And the propagate for bit 0 is just a 0 because you don't have any previous value. Propagate is just 0. And then the sum for bit, like a single bit, is the propagate for that single bit XORed with the generate from that, basically the bit before it all the way down to 0. So the sum, obviously, you need to look at what all of the previous bits, whether you have a carry propagating through all of the previous bits, because that generate from I minus 1 to 0, so the previous bit down to 0, that generate value is basically the carry value that propagated all the way through all the previous bits. And so your sum is going to be your propagate XORed with your generate of all the previous bits. So let's look at how this might work as far as our total logic that we're trying to compute our sums and carries if we had a 4-bit adder. So what we can do is for any given bit, based on the logic that we were talking about in the previous foil, you can calculate, like we look at the first bit, we can calculate propagate 1 and generate 1 for the first bit just based on the A and B values, so A sub 1 and B sub 1. So A XORed with B give us our propagate 1, and A and with B gives us our generate 1. And likewise, you can do that for each of the 4 bits. So with just one stage delay for your propagate and generate for every single bit, they can all be done in one stage delay, and propagate 1 and generate 1 all the way through propagate 4 and generate 4 are all calculated and sitting there waiting for the carry logic to eventually propagate through, or to go through this this row called group PG logic. So you have some additional logic that you need to do to generate your G0, G1 through 0, G2 through 0, and G3 through 0. So you need to calculate those combinational generate 3, 2, 1, 0, and then based on that you get your carry out 0 through carry out 3, and then finally at the bottom there you see the sum logic, which is waiting for, it basically depends on the propagate for each individual bit and then the carry bit to come through the PG logic in order to generate our sum, and then our final carry out depends on basically the bit 4 propagate as well as the generate from bit 4 and the generate from all the previous bits. So that gives us the logic that we need, and we just need to look at what happens, how do we do that group PG logic in the middle in order to make this functional adder. Here we can see, based on the function that we talked about a couple slides ago for what's the function for the generate of I through 0. This is the logic that we need for the PG function row that we had kind of blocked out in the previous foil. So if we go back 2 foils ago, we had the equation that G of I colon 0 would be G sub I ORed with P sub I, that the P sub I is ANDed with G sub I minus 1 colon 0. So this is how you could implement that function in the middle row that's shown there, where you get G sub 0 just goes straight through to give us C sub 0, but G sub 1 colon 0 needs to take the generate of 1 along with the propagate of 1 and G sub 0 in order to do, the propagate of 1 is ANDed with G sub 0 colon 0, and then that is ORed with G sub 1 in order to give us G 1 sub 0, 1 colon 0. That G sub 1 colon 0 is now our carry sub 1 coming out of this PGK functionality, but that is also G1 sub 1 colon 0 that goes on to the next bit in order to help calculate G2 colon 0. And you can see again the equation for G2 colon 0 is G sub 2 ORed with the combination of ANDing P sub 2 with G sub 1 colon 0. And then likewise that goes into the next bit, and we just continue on there. And you can see how if you have a C1 or our carry in, C in, goes into bit 1 to produce G1 colon 0, and then that ripples on to bit 2 to create G2 colon 0, and that ripples on to bit 3 to create bit 3 colon 0. And this again is called a carry ripple function. It just ripples from bit to bit. So you can see this is what I was talking about several foils ago, where I was saying this particular type of function, every bit, the carry has to continually ripple through bit to bit to bit. And you can see where your critical path is this carry rippling through. Now it's just rippling through a smaller amount of logic because we've calculated the propagate and generate already, and so we don't need to calculate A and A bar for each bit, but we have that propagate and generate that we're using instead for each bit, and then rippling the carry through. But this design still causes us to have a full, for every bit of the A and B data, you have one extra stage delay of your carry rippling through your adder. So you can see that this overall design, as is, would be a fairly slow and waiting for the carry in order to end. So we've been talking about a carry ripple adder for the most part. So let's see how the actual delay could be calculated going through a 16-bit 15 colon 0 for a carry ripple using this type of propagate generate functionality that we've been talking about in the previous few slides. So this is kind of trying to, on the right hand side, just show pictorially how the boxes are one of those kind of PGK functions for per bit, and then the connections are showing how at the output of a given bit you have to have the carry in go into the next bit, and so you propagate through, and then the Y dimension is showing us basically the delay that you have going through each of those stages. So here we can see the equation for the full delay going through this full chain would be a T sub PG. That stands for going through the initial, like bit 0 or bit 1, for bits A and B, or your data values of A and B, you have to go through to generate P sub 1 and G sub 1. So your PG calculation, you have to go through one of those at the very beginning. Then you go through n minus 1 of the and or gates that produce your generate for generate of I colon 0. And so you have n minus 1 of those. So the t sub AO is the time going through that generate and or function delay. And then finally at the very end, you have an XOR function that XORs your generate going all the way through the chain with the propagate at the final bit. And so that gives you the total time to go through a carry ripple PGK type adder. So one original PG generation at the beginning, one XOR at the end, and then n minus 1 of the and or functions of the carry rippling through. Before we go on to the next foils, I just want to make a short comment on some of the notation that we'll be using going forward. So we're going to be looking at diagrams that have a couple different types of cells in them. When we look at a diagram that has a black cell, so fully black, that's something that will have generate and propagate coming in, and it will produce a generate and propagate going out. If we have a more hashed type cell that's in gray or other colors, if it's not full black, it'll have the generate and propagate coming in and just generate going out. And if we show a buffer, that basically means we're just buffering either the generate value or the propagate value. Whatever's coming in is what's going out on a given bit. So just keep that notation in mind for the upcoming foils. As we've said many times before, a carry ripple adder is basically slow, and we have to go through all n stages. So if we have a 16-bit adder, we have to go through every single stage and go through a ripple through that stage, so we get 16 times our delay through the output. So below is a figure that kind of denotes how we could make a faster type of adder. And this is what's called a carry skip adder. In effect, you can lump bits in groups of bits instead of creating or having each bit be its own, and you just carry through each bit. You can lump the bits together and say, so the example below is, let's say we have 16 bits and we're lumping in them in groups of 4. So what we can do is we can take groups of 4 and calculate based on just that group of 4 what would our propagate value be if based on that group of 4. And so all of our propagate values, so propagate 4 through 1 can be calculated just based on bits A and B for 4 through 1. Propagate 8 through 5 can be a propagate that's only based on the A and B values of 8 through 5, etc., all the way up to 16 through 13. Each group of 4 can generate a propagate based on that. Now, when we have our Cin come in from the very right hand side, it comes in, we've calculated propagate 4 through 1. Now based on Cin, we can determine whether C out goes out to basically C of bit 4, and now C sub 4 just goes through a single delay to go into and be compared with the value of propagate 8 through 5. Since propagate 8 through 5 could be calculated at the same time as 4 through 1, it should now be sitting there waiting, and as soon as C4 comes through, it goes through and gets compared to 8 through 5. And now you can see we just go through a single delay for a group of 4 bits. and then we go through that delay and we get propagate or our carry out for bit 8, and it just goes through a single delay. It's got the propagate 12 through 9 waiting for bit 8 already, so it can go there, get compared, and produce a carry out for bit 12 with just a single delay. So you can see as the carry is going through, the carry is only going through a single delay element for every 4 bits instead of a single delay element for every bit. And so this can actually reduce your delay through the full 16 bits by a fairly decent factor, and we'll look at that in the next foil. So now let's look kind of pictorially at the carry skip adder delay diagram that we were talking about in the previous slide from a logical point of view in the previous slide. So let's say we have k number of groups that have n bits each in their group, and our total number of bits, capital N, is equal to small case n times k. So in this case, and what we had in the previous foil, we have 4 groups of 4 bits each. So both k and n are 4. You can see if we look at the graph, the longest path that we have, if we're starting up at bits 0 or 1, is if we start at bit 1 and we go down and to the left, we have to go through 3 gray boxes to get our carry going through to our carry 4 sub 0. And at this point, you can see that that carry coming out of bit 4 is being calculated at the same time and in parallel with the carry that's going to come out at bit 8, the carry coming out at bit 12, and the carry coming out at bit 16, or I should say the generate bits. So that will go through 3 boxes, and it will hit the mux looking box there that's in white and go through that delay. Now at this point we can look what's the longest delay from this point. We can either go through 3 blue boxes or we can go through more to the left. So the longer delay is going to be if we go from the white box and skip over to bit 8 where we're hitting another white box. That value is waiting for us, so it's basically the delay coming through from bit 4 goes straight through that white box at bit 8 and then goes to the left and hits bit 12, and at that white box at bit 12 we now have 2 potential choices to get to the end. One is the white box at bit 16, but that is a shorter delay than going through the final 3 bits where we have to calculate the carry propagating through bits 13, 14, and 15. So at the bottom there we have 3 carries that we need to go through. At the very top we had 3 that we needed to go through, and then we had the 3 through the 3 white boxes in the middle where we were skipping each set of 4 bits. So the total time delay through our carry skip adder is similar to what it was for the ripple adder, where at the very beginning we have 1 delay going through our initial propagate and generate for each individual bit. At the very end we'll have a XOR function that we need to do for the final sum, which in this case is up at bit 15, and then in between we have an AND OR function that we need to do, and the total number of AND OR functions that we go through are the ones for basically the ones related to each bit of each group of 4. We have 3 at the beginning and 3 at the end, so that's n minus 1 times 2 AND ORs that we're going through for the gray boxes in the upper right and the blue boxes in the lower left. And then we have k minus 1 AND OR functions that we're going through for the 3 white kind of mux type boxes in the middle. So the total number of and/or functions is k minus 1 plus n minus 1 times 2. So the total delay, if we add it all up, in this particular case, our n is 3, so n is 4, so n minus 1 is 3, times 2 is 6. K is 4, so k minus 1 is 3. So we add the 3 to 6, we have 9 and/or functions, and then we have the TPG and TXOR. So this compares to the ripple adder. The ripple adder had the same beginning and end, TPG and TXOR, but it had 16 and/or functions. So this is 9 instead of 16. So you can see it's an improvement. It's not a huge improvement, but it is an improvement. If, on the other hand, let's say we had a 64-bit adder and we broke it up into 8 groups of 8, instead of going through 64 for a ripple adder, the carry skip adder with an 8 and 8 would give us 8 minus 1, 7 times 2, plus an additional 8 minus 1 is 7. So 14 plus 7 would be 21 and/or functions instead of 64. You can see where that, in a 64-bit adder, you'd get almost a factor of 3 better in delay timing through it. So as you get larger and larger adders, this has a great benefit. For smaller adders, it's not. Now, a variation on a carry skip adder is a carry skip adder with variable group size. So the one we looked at in the previous slide, we took 16 bits and we broke them up into 4 groups of 4-bit segments. And we saw that at least for a 16-bit adder, it improved our delay from 16 stages down to 9, which is relatively decent. But in this particular scenario, you can see we actually have broken up into one additional group, but we've varied the size of the group. So we have larger groups kind of in the middle and a little bit smaller on the outsides. And if we look at pictorially the diagram here, you can see how that's helped us. So if we start in the upper right corner again, and go through from bit 1 to 2, we're just going through a single carry stage there, and then we're hitting one of the skip stages that's in white there. Now we go through that skip stage and we start going through our skip stages till we get to the second to the last skip stage. You can see we go through one at bit 2, second one at bit 5, third one at bit 9, and a fourth one at bit 13. And then at this point, our longest delay is through the final 2 blue carry stages at bits 14 and 15, and then we get to the end. So if we add up the total number of stages there, we'll see the 1 gray at the beginning, and then 4 of the white brings us up to 5, and then 2 blue at the far left corner. And that brings us up to 7 total and/or stages. So now we're at 7 stages, whereas the design in the previous slide was 9 stages, and the full carry ripple adder was 16. So at 7 stages, we're now less than half the number of and/or stages than we had in the carry ripple of 16. And so this is actually one of the a faster design than just breaking up your bits by equal number of bits per grouping. And if you do this for larger adder sizes, so if we went up to 64-bit, like I mentioned in the previous slide, the delay will grow as a square root of n. So from 16 to 64 is a factor of 4 growth. The delay in this adder would only grow by a factor of 2. So the 7 stages we have here might go up to 14 instead of the 21 that we calculated. So this is a decent way to take the carry skip design and improve on it and get even better delay through your stages. even though it's a little bit more complex to create, since instead of creating one group that's the same for every group of bits, you now need to create variable length PG. Your generate equations are going to be a little bit more complex because you're going to need a larger variety of them. So it trades off better delay for a little bit more complexity in your design.